Hi everybody, welcome back to Statistics. Today we're in section 8.1 talking about the distribution of the sample mean. We're going to discuss the distribution of the sample mean for normal populations, and we're also going to discuss the distribution of the sample mean for non-normal populations. And in this section we will get introduced to a very important idea called the central limit theorem. Up to now, we've only been able to calculate probabilities and make predictions for normal populations, but the central limit theorem is going to show us a way that we can also work with non-normal populations. So that's going to make inferential statistics a lot more useful for us. So it sounds pretty important, so let's get started. First, remember from Chapter 6 that a random variable is a numerical measure of the outcome of a probability experiment. For example, each month the government surveys 250,000 households about lots of things, one of which is household income. Now, because the participants in the survey are randomly selected and household income is numeric, household income then becomes a random variable and we can find its mean. For example, the mean household income for 2009 was $67,976. Of course, another sample taken at another time would likely be a little different, and the next one a little different still. And no two samples are guaranteed to yield the same sample mean. Now, since the government collects a sample mean each month, the sample means themselves can be thought of as a random variable. The probability distribution for all possible values of a statistic computed for a sample size of n is called a sampling distribution. The sampling distribution of the sample mean x bar is the probability distribution of all possible values of the random variable x bar computed for a sample of size n with a population mean mu and a standard deviation sigma. So the sampling distribution of the sample mean is just the probability distribution for all possible values of x bar for a certain size sample. And we can calculate the mean of that probability distribution, and we can calculate its standard deviation. Now the mean of the sampling distribution of the sample mean is written mu sub x bar. That's a mu with a subscript of x bar. You already know the population mean is written mu. Now the subscript of x bar is so that we don't get confused whether we're talking about the mean of the population or the mean of the sampling distribution. And the standard deviation of the sampling distribution of the sample mean is called the standard error, and it's written as sigma subscript x bar, and we usually just say sigma sub x bar. So again, mu sub x bar is the mean of the sampling distribution of the sample mean, and sigma sub x bar is the standard deviation of the sampling distribution of the sample mean. But instead of saying standard deviation of the sampling distribution of the sample mean, which is quite a mouthful, we just call it the standard error. Now there are two situations we can talk about. Either the original population is normally distributed or it's not normally distributed. First, let's talk about what happens if the original population is normal. So if the original population is normal, then for any sample size, the mean of the sampling distribution of the sample mean is equal to the population mean. In other words, mu sub x bar will be equal to mu. Also, the shape of the sampling distribution of the sample mean is normal. So that's very important. If the original population is normal, then for any sample size, the shape of the sampling distribution of the sample mean is also normal. That's actually kind of cool if you think about it, and in just a minute I'm going to show you an applet that will be like a visual aid to help you understand what's really going on here. Also, the standard deviation of the sampling distribution of the sample mean is always less than the standard deviation of the original population. In other words, sigma sub x bar is always less than sigma. So mu sub x bar is always equal to mu, but sigma sub x bar is always less than sigma. In fact, the larger the sample size is, the smaller the standard error will be. Sigma sub x bar is actually equal to sigma divided by the square root of n. So the larger n is, the smaller this quotient is, and therefore the smaller the standard error is. Now what I would like to do is use an applet that comes with your book. You can access this applet yourself if you would like to. It's under Tools for Success. Just log into My Labs Plus, click on Tools for Success, then go to the Review section and click on Applets, and after you've clicked on Applets, click on Sampling Distributions. You will get this page. I have changed my distribution type to bell-shaped. By default it comes up uniform, but I have changed it to bell-shaped. Now what we've got here is a population that is of course bell-shaped. The mean of this population is 25, and the standard deviation of this population is 5. Now what's going to happen is I'm going to get samples of size n equals 5 from this population. For each individual sample we do, the members of the sample will show up here. There will be 5 of them. And for that sample of n equals 5, we will be able to calculate a mean. So now the mean of our sample will show up here. And down here on this bottom graph, we will collect all of the sample means. So what's going to happen is that this is going to become a sampling distribution of sample means. Here you'll be able to see how many samples we've taken, and here you'll be able to see the mean of the sampling distribution of the sample mean. In other words, this line represents mu sub x bar, and here you'll be able to see the standard deviation of the sampling distribution of the sample mean. In other words, this line represents sigma sub x bar. Okay, so let's do it. Let's have the computer pull one sample for us. You can see here are our 5 values. The mean of our 5 values is 23.06, and that shows up here, 23.06. There's only been one sample taken so far. Now let's get another sample. For our second sample of 5, these are the values. The mean of our second sample is 25.8. And now down here, so far we have 2 samples. Both sample means are showing here. And the mean of our sample means is 24.4. And the standard deviation of our sample means is 1.9396. Okay, now let's have the computer pull 1,000 samples for us. So we're not going to see each individual little box fall down, but that's okay. The 1,002nd sample we got is showing here. The collection of all 1,002 sample means is showing here. You can see that this population is not perfectly bell-shaped, but it is roughly bell-shaped. And notice that the mean of our collection of X bars is 24.95, very close to 25. And notice that the standard deviation of our collection of X bars is 2.1907. Now the question is, what should we have expected this to be? Well, remember that when you have collected every possible value for X bar, the mean of the sampling distribution of the sample mean is equal to mu, and the standard deviation of the sampling distribution of the sample mean should be sigma divided by the square root of n. So we know that sigma is 5, and we also know that the sample size is 5. So we could calculate 5 divided by the square root of 5, and sigma sub x bar should be 2.236, and that's very, very close to this value. but we've only run 1,000 samples. Let me run a few thousand more samples. Now I have a total of 4,002 samples. Notice that the distribution is even a better bell shape than it was before. Notice that the mean of our collection of X bars is even closer to 25 than it was before. And notice that the standard deviation is even closer to 2.236 than it was before. And if I run a few thousand more samples, we'll see that it gets even closer. So with 7,000 samples, I can see that the mean of my collection of X bars is 25.012, and the standard deviation of my collection of X bars is 2.238, and I was expecting 2.236. So this is very, very, very close. So what do I really want you to take away from this? I want you to understand that if the population is normally distributed, then no matter what the sample size is, the mean of all the sample means should match the population mean. And the standard deviation of all the sample means should match the population standard deviation divided by the square root of the sample size. Now let's look at an application problem together. This says the IQ(x) of humans is approximately normally distributed with a mean of mu equals 100 and a standard deviation of sigma equals 15. Compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. That is, compute the probability that X bar is greater than 110. So notice that they told us that our random variable is approximately normally distributed. And what that means is we can count on the sampling distribution of the sample means to be normal as well. And since the sampling distribution of the sample mean is going to be normal, we have permission to use our z-table to find this probability. So it's very important that they told us that the population is approximately normal. Now we can approach these very similarly to the way we approached the ones in section 7.2. What we want to do is calculate a z-score for this X bar and then use that z-score to find an area, and that area will be the probability that we're after. Now when we calculate our z-score, we don't need to use mu and sigma. We'll need to use mu sub X bar and sigma sub X bar, because we're not calculating the z-score for just a single X, we're calculating the z-score for an X bar. So we know that mu equals 100, they told us that in the problem, and therefore we know that mu sub X bar equals 100. And they told us in the problem that sigma equals 15 and n equals 10, therefore we know that sigma sub X bar equals 15 over square root of 10. Now I want you to resist the temptation to turn this into a decimal approximation, because if you punch this into the calculator now and get a decimal approximation, you will end up rounding off decimal places. And if you use those rounded off values to calculate the next answer, then it's going to cause problems somewhere down the line. So it's best if you leave this in exact form. Okay, now we're ready to calculate z. So for X bar equals 110, z is going to be X bar minus mu sub X bar divided by sigma sub X bar. That's going to be 110 minus 100 all over 15 over square root of 10. Now let me show you how I enter this in the calculator. You see, it's very important that you get this into the calculator using the correct order of operations. And what this says is that this difference should be divided by this quotient. And I don't want to have to get a decimal approximation anywhere along the way, because I don't want to have to round off and then use that rounded off number to do another calculation. So now there's no doubt that you can do this subtraction mentally, but if you couldn't, you would enter 110 minus 100, and press enter. It's very important that you press enter there and actually see that difference on the screen. And then we need to divide by this whole quotient. The problem is, if you don't put this in parentheses, it will divide by 15, and then it will divide that answer by square root of 10. That's not what you really want. What you want is for it to divide 10 by this quotient. So we need to tell the calculator that we want to divide that 10 by the total of 15 divided by the square root of 10. And so our z-score ends up being 2.11. Okay, now we want to sketch this z-score on the standard normal curve. So I've drawn myself a standard normal curve here, and now they've asked us to find the probability that x bar is greater than 110. And now, since they've asked us to find the probability that x bar is greater than 110, what we want to do is draw the z-score 2.11 on here and shade the values that are greater than that. So this is the area that I'm looking for, and you can see that it's a fairly small piece of the area under the standard normal curve. At this point, you would go to the z-table and find the area to the right of 2.11, and the table says that that area is 0.0174. So the probability that x bar is greater than 110 is 0.0174. Now, I want you to think about this. Even though the work we're doing feels the same, the question they've asked us is very different from the one before. Back in section 7.2, they would have asked us, find the probability that a randomly selected person has an IQ greater than 110. Here they're asking us to find the probability that a sample of 10 people has a mean IQ score greater than 110. So it may not be very unusual at all to find a person whose IQ is greater than 110, but it would actually be very unusual to find a group of 10 people whose mean IQ score is greater than 110. That's a very different question. And the larger the group of people gets, if n went from 10 to say 20, the probability would drop even more. So the larger n gets, the harder it gets to find a group of people whose average score is this far away from the mean. Now here is an exercise from the homework. This says the reading speed of second grade students is approximately normal with a mean of 90 words per minute and a standard deviation of 10 words per minute. What is the probability that a randomly selected student will read more than 95 words per minute? Well, this is the kind of question they were asking us back in section 7.2. So to find this probability, all we would do is say that mu is 90 and sigma is 10, and we would then calculate a z-score. We would say that for x equals 95, z equals 95 minus 90 all over 10, and that's going to be 5 over 10 or 0.5. Now we would sketch our z-score of 0.5 on the standard normal curve, and since they asked us to find the probability that a randomly selected student reads more than 95 words per minute, we will shade to the right of that. And now we will go to the table and find the area to the right of 0.5, and that area is 0.3085. So the probability that a randomly selected second grade student reads more than 95 words per minute is 0.3085, or about 31%. But now part B says, what is the probability that a randomly selected sample of 12 students will read more than 95 words per minute? Well, now we're not just talking about mu and sigma, but we need to calculate a z-score using mu sub x and sigma sub x. So given that mu is 90, we know mu sub x bar is also 90. And given that sigma is 10 and n is 12, we know that sigma sub x bar would be 10 over the square root of 12. Now, algebraically, this could be simplified, but we are only interested in decimal values, so there is really no benefit to simplifying this. Don't even worry about it. But now we want to find a z-score for x bar equals 95. So for x bar equals 95, the z-score is x bar minus mu sub x all over sigma sub x. And that's going to be 5 divided by parentheses 10 over square root of 12, and that is approximately 1.73. Now if we draw a standard normal curve and we put our z-score there, 1.73, and we shade the area to the right of that, the table tells us that the area to the right of z equals 1.73 is only 0.0418. So the probability of randomly selecting a group of 12 second graders whose mean reading score is greater than 95 is only 0.0418. But the probability of randomly selecting a single second grader who can read more than 95 words per minute is much greater. That probability was 0.3085. Okay, so now we're very familiar with the fact that for normal populations, the sampling distribution of x bar is normal, regardless of sample size. And we know that the mean of the sampling distribution of x bar equals the population mean. And we know that the standard deviation of the sampling distribution of x bar equals the population standard deviation divided by the square root of n, which is sample size. But now we have to ask, what about non-normal populations? What does the sampling distribution of x bar look like for populations that are skewed or uniform? You know, it was really important for us to find out that the sampling distribution of x bar had a normal shape, because knowing that the sampling distribution of x bar is normal allows us to use the z-table to answer questions about probability. But if we don't know that a distribution is normal, then we can't use the z-table. So it's important for us to know what the shape of the sampling distribution of x bar is for a non-normal population. That brings us to the central limit theorem, which says, regardless of the shape of the underlying population, the sampling distribution of the sample mean becomes approximately normal as the sample size n increases, and mu sub x bar will equal mu, and sigma sub x bar will equal sigma over the square root of n. This is actually a pretty amazing result. I don't imagine it was that big of a surprise to you that the sampling distribution of x bar is normal when the underlying population is normal. But to find out that the sampling distribution of x bar is normal even when the underlying population is not normal, that is pretty amazing. Now notice that it says the sampling distribution of x bar becomes approximately normal as the sample size n increases. So now we have to ask, how big does n need to be in order for us to know for sure that the sampling distribution of x bar will be normal? And here's the answer. If the original population distribution is not normal, then the shape of the sampling distribution of the sample mean is guaranteed to be normal only if n is greater than or equal to 30. So the bottom line is that in order to use the z-table to answer questions about probability, we either need to know that the shape of the distribution of the underlying population is normal, or if we don't know that the shape of the distribution of the underlying population is normal, then we need for n to be at least 30. Let's go back to the applet and I'll show you what we're looking at. Here I am back in the sampling distribution applet from MyLabs Plus. Notice that this time I have a right skewed population. So here is the distribution of our population, and it is definitely right skewed. It has a mean of 14.05 and it has a standard deviation of 11.83. Now again, we're going to have the computer pull samples from this population and then collect all of the sample means down here, and we want to see the shape of the distribution of our collection of x bars down here. Now I have the sample size right now set at 5. Let's go ahead and have the computer run 1,000 samples for us. And here you see a collection of 1,000 X bars. Notice that the shape of this distribution is somewhat right skewed, which is kind of not surprising since the original population was definitely right skewed. Let's see what happens if we take a few thousand more samples. Okay, so now I have a total of 4,000 samples, and you can see that this is a more normal shape than it was before, but it's still somewhat right skewed. Notice that the tail on this side is a little longer than the tail on the left side. Now let's see what happens if we increase our sample size from 5 to 10. And we'll take 1,000 samples. Now at 1,000 samples, the distribution of this collection of X bars is a lot closer to normal than the one we saw when our sample size was 5. So just increasing the sample size a little bit gave us a more normal collection of X bars. Now I'm up to a total of 6,000 samples of size 10, and you can see that the distribution of this collection of X bars is still a little bit skewed right, but it's a lot closer to normal than when we started. Now let's go ahead and take the sample size all the way up to 30. When I take 1,000 samples with a sample size of 30, right off the bat, the distribution of our collection of X bars is almost perfectly normal, but notice how small the standard deviation is compared to the standard deviation of the underlying population. That's because the standard deviation of the sampling distribution of the sample mean, or what we call standard error, is equal to sigma divided by the square root of n. And here n is quite large, n is 30. And so dividing by the square root of this large number is causing us to have a fairly small standard error. Let's see what happens if we take a few thousand more samples. Notice that it hasn't changed all that much because it was already pretty close to normal. Notice that the mean of our collection of X bars is very, very close to the mean of the population. And notice that the standard deviation of our collection of X bars is very close to what we would get if we took this standard deviation and divided by square root of 30. In fact, 11.8255 divided by the square root of 30 is 2.159, which is very close to this standard deviation that we're seeing here. And if we let n get very large, like up to 100, if we take 1,000 samples, notice that the distribution of this collection of X bars is bell-shaped, but very narrow. It has a very small spread. That's because we're taking this standard deviation and dividing by the square root of this sample size. So 11.8 divided by the square root of 100 would be 1.18, and that's very close to what we see here. But the spread here is not very big at all, and it just makes sense that the larger the sample size gets, the more unusual it becomes to find a sample whose mean is very far from the population mean. Now let's look at a couple more examples together. This is example 5 from your text. This says the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2 pounds. What is the probability that a sample size of n equals 35 would have a mean weight gain of 36.2 pounds or more? The first thing I want you to notice is that the population we're dealing with has a distribution that is skewed right. Therefore, we could not use the z-table to find the probability that one randomly selected patient would have a weight gain of 36.2 pounds or more. We can't do that because the distribution is skewed right. However, the central limit theorem tells us that as long as n is greater than or equal to 30, the sampling distribution of the sample mean will be normally distributed, and therefore we can use the z-table to find probabilities. So, knowing that this distribution is skewed right, it's important for us to have n of at least 30, and we do have n equals 35 here. So let's go ahead and write down that the mean of the population is 30, therefore mu sub x bar is also 30. Sigma is 12.9 and n is 35, therefore sigma sub x bar is 12.9 over the square root of 35. Okay, the next thing to do is to translate this x bar of 36.2 into a z-score. So I'll say x bar of 36.2 leads us to a z of 36.2 minus 30 over this sigma sub x bar. Put that in your calculator. Remember, you do the subtraction first and press enter, and then divide by this quantity in parentheses. And we're going to get approximately 2.84. Now let's sketch this on our standard normal curve. So here's a curve. 2.84 would be out here somewhere. And since we want to know the probability that this sample could have a mean of 36.2 or more, we will shade the area to the right. Now that's not much shading, so we expect the probability here to be fairly small. And if you go to your z-table and look up the area to the right of 2.84, you'll find that that area is 0.0023. So the probability of the sample mean being greater than 36.2 is only 0.0023, quite small. Okay, now the question is, knowing that the probability of having a sample mean greater than 36.2 is so small, does this suggest anything unusual? And the answer is yes, this does tell us something unusual. Either we happen to choose a sample with an unusually low mean, which is possible but not very likely, or the mean weight gain for low-income patients is actually more than 30 pounds. Number 2 is much more likely. The probability of number 1 happening is only 0.0023. What's more likely is that mu is not actually 30, it's actually something larger than 30. And here is an exercise from the homework. This says the shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. However, records indicate that the mean time for an oil change is 11.4 minutes and the standard deviation for an oil change is 3.2 minutes. And part A says, to compute probabilities regarding the sample mean using the normal model or the z-table, what size sample would be required? Well, we know from the central limit theorem that the sampling distribution of the sample mean is not guaranteed to be normal unless n is at least 30. So in order to use the z-table to work on probabilities like this when we don't know the shape of the original distribution, we need n to be greater than or equal to 30. Now part B asks us, what is the probability that a random sample of n equals 40 oil changes results in a sample mean time of less than 10 minutes? Now we know that since n is greater than 30, we can use the z-table to find this probability. So let's go ahead and write down what we know. We know that since mu equals 11.4, mu sub x bar will also equal 11.4. And we know that since sigma is 3.2 and n is 40, sigma sub x bar will be 3.2 over the square root of 40. Now we can find a z-score for x bar equals 10 minutes. So when x bar equals 10, z equals 10 minus 11.4 over 3.2 over square root of 40. And putting that in the calculator, we find that z is approximately negative 2.77. Now we want to sketch this on our standard normal curve. So I'll draw a curve, and negative 2.77 will be way over here to the left, and we want to find the probability that x bar could be less than 10 minutes, so we'll shade the area to the left of that z-score. And if you look at your z-table now, you'll find the area to the left of negative 2.77 is 0.0028. So the probability that x bar is less than 10 is 0.0028. Now part C. Suppose the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, The oil change facility will perform 40 oil changes between 10 and 12. Treating this as a random sample, what mean oil change time would there be a 10% chance of being at or below? This will be the goal established by the manager. Okay, so this time, instead of asking us to find a probability, they're giving us an area and they're asking us to find the time associated with it. So here's what we're trying to find. We want to know what time is required so that the probability of being at or below that time is 0.10. So let's start by drawing a standard normal curve, and I'll shade the 10% of area that's on the left. This is the 0.10 that they gave us in the problem, and this z-score is what we need to find. So using that area and going to the z-table, you'll find that the z-score that has an area of 0.1 to its left is negative 1.28. Now, to turn this back into an x value, you remember this formula x equals z times sigma plus mu? Well, here we're not really looking for x, we're really looking for x bar. So we won't use mu and sigma, we'll use mu sub x bar and sigma sub x bar. So x bar is going to equal z times sigma over square root of n plus mu, and plugging our known values into the formula, we'll get negative 1.28 times 3.2 over square root of 40 plus 11.4, and the average time they need to beat is about 10.75 minutes. So to sum up, if a population is normally distributed, then the sampling distribution of the sample mean will also be normally distributed. But if a population is not known to be normally distributed, then the sampling distribution of the sample mean is approximately normal only if n is 30 or more. But regardless of sample size, the mean of the sampling distribution of the sample mean is equal to mu, and the standard deviation of the sampling distribution of the sample mean is equal to sigma over square root of n, and sigma sub x bar is also known as standard error.